All right, welcome to lesson 7 entitled Solution Properties. In lesson 7, we started off by looking at something called Beer's Law. And Beer's Law, we learned, says that the absorption of a certain solution is equal to some intrinsic properties, structural properties of that solution, multiplied by the distance the light has to travel through the solution, multiplied by the concentration. And we got at that by looking at two different concentrations. Let's look at one of the most significant examples of that. When we took a solution here where we put 100 milliliters of pure Smurf blood and looked at it horizontal, it looked, let's say, like that. And when we put 100 milliliters of pure Smurf blood in this one, it also looked identical. Okay? And it looked identical vertically and horizontally when we look through it. And then we took one of these and we changed it. We added 100 mils of water to it. And looking at it horizontally, it got lighter. But looking at it vertically, it did not. Okay. So what we lost in concentration, we gained in path light. Saying it in a simpler way, we dropped the concentration by half by adding water, but subsequently we increased the path length by a half. And because the molar absorptivity here was constant, the absorption stayed the same. So we're going to look at some notes here. We're going to take a look at this equation here, the Beer's Law equation, and we're going to unpackage what we mean by concentration. And concentration in chemistry is called molarity. And molarity has a symbol M. And the equation for molarity is moles divided by liters. But it's not just moles divided by liters. It's the moles of the solute particles, what you're putting in there, divided by the total volume of the solution. That's the volume of the water, since we're talking about aqueous solutions, plus the space that these solute particles are occupying as well. So let's look at how we speak this, because there's a certain way of talking about it. So let's say we have a solution of HCl. So 6MHCl, and you often hear students saying that, but I don't want you to say 6MHCl. When you see that big M, that's the concentration. That means 6, and I want you to say molar HCl. It has a molar concentration of 6. What does that mean? That means that there's 6 moles of HCl dissolved in every 1 liter of total solution. That's exactly what that means. That also means that there are 6 moles of H plus dissolved in every 1 liter of solution. And that means that there's 6 moles of Cl minus dissolved in every 1 liter of solution. And we see that because for every 1 HCl, there's also 1 H and 1 Cl. Let's look at a situation where that's not always true. Let's say we had 6 molar solution of sulfuric acid, H2SO4. So again, we'd say 6 molar H2SO4. Okay. And what that means is you have 6 moles of H2SO4 dissolved in every 1 liter of solution. Okay, but what if I were to look at the concentration of the H's instead? Okay, well, that also means that you have 6, I'm actually going to erase that. That means that we have 12 moles of H plus per every 1 liter of solution. Okay, let me show you how I got at that. Okay, so I'm going to do the work down here below. I'm going to do this one all in red. So if I have 6 moles of H2SO4 per every 1 liter, I'm going to do a little conversion factor. I don't want to mess with the liters, but instead of getting moles of H2SO4 for every 1 liter, I want to get the concentration of just the H. So for every 1 mole of H2SO4, we have 2 moles of H plus. And that yielded 12 moles of H plus per every 1 liter of total solution. And that's where that came from. It's the same thing as saying, you know, for every 1 mole of Ramsey's, here's Ramsey, kind of bald, they got these big lips, they're equal to 2 arms. Well, for every 1 H2SO4, there are 2 H pluses, okay? So let's look at some just equation manipulation stuff. When you look at the molarity equation, that's ghetto. When you look at the molarity equation, they're often going to ask you for grams or give you grams. And out of all of these 3 variables, grams is going to come out of the moles using molar mass. It makes sense. And sometimes they're going to ask you for milliliters or give you milliliters. And that's going to come off that liter. And just remember here that there are 1,000 milliliters in every 1 liter. So let's go ahead and look at an example of a problem like this. Okay, here they say, what mass? And when they say mass, they mean grams of KBr, and they went ahead and gave you the molar mass, is required to make a 250 milliliter solution with a molarity of 0.4. So we saw this big M. That means we're going to write the molarity equation. They're asking for mass, so we know that that's going to come from moles. So let's rearrange this. Moles equals molarity times liters. Let's go ahead and plug in what we know. That's 0.44. And the liters comes from here. We know that 250 milliliters divided by 1,000 is 0.250. And that's going to yield 0.10 moles of KBr. Now, they want the grams, so they gave us the molar mass there. For every 1 mole, there's 119 grams, and they made the mass really easy for us to calculate because they made it just a simple fraction of the molar mass. And that's how we did it. And that's how we got this answer of D, 11.9. Let's look at a different variation of a problem. Here they say we have solid aluminum nitrate, and it's added to water. And they say that we end up with a concentration of NO3-, which is 0.10. And by the way, when you see things in concentration or in brackets, like if I had bracket stick figure, I mean the concentration of 6 stick figure. So bracket NO3- means just the concentration or molarity of NO3-. So let's redefine this. 0.10 moles of NO3- per every 1 liter of total solution. But they want to know the concentration of the aluminum ions. So let's do a simple conversion like I showed you. Let's leave liters alone, and let's look at the relationship here. Well, there are 3 moles of NO3- per every 1 mole of Al3+. So 0.1 divided by 3 is going to give us B, 0.033 molar. Let's go ahead and look at this last one. It says you have 87 grams of K2SO4. They gave you the molar mass, and they told you that it's dissolved in enough water to make 250 mils of total solution. And they want to know the concentration of not the K2SO4, but the concentration of the K plus and the concentration of the SO4 2-. Okay. So I suggest that you find the molarity of the K2SO4 first by converting those 87 grams to moles and popping that right here, and converting those 250 milliliters to liters, popping that right here. And then looking at the relationship between the K2SO4 and the K plus, and the SO4 2- and the K2SO4. Thanks a lot.